So Heap Sort is a really interesting sorting algorithm because it uses a data structure called a heap, which is essentially a tree with a few restrictions. Um, First of all, I better explain what a heap is more properly than that. So at the beginning of your tree, you have the root node R. And in a normal tree, you can have as many children as you want, but this parent node R can only have two children. In fact, any parent node can only have two children maximum. So let's give it two children, child 1 and child 2. Now the other rules of a heap is that, first of all, it's limited to two children. I've already stated that, and the value of the child must be less than or equal to the value of the parent. So each of these nodes will store some value. Say this is 12. Actually, I'll write that in a different color. Say the root node is storing the number 12. That means that C1 and C2 must store a value that is less than 12, say 9 and 3. Now each of these can also have children. You can have as many not as many branches, you only have 2, but as many children. The heap can be as big as you want. Let's call it C1, C11, and C12. These ones here must be less than 9. I'll give that a big tail. So let's say 2 and 1. Now, this one can also have children, and now, okay, so this is our heap structure. Now, the rules of adding to a heap. Well, say we want to add the number 2 to a heap. We want to add the number 2. Well, we can just add it on the end. We go in by row along here, and we look this row along here. The parent of the first parent in this row along here already has 2 children, right? So the second parent in this row along here does not have any children, so we can assign that a child. We can give that C21, and that will hold the number 2. And now we check for violations of the heap structure. Well, 2 is less than 3, so that's fine. We don't have to do anything. Now, we always add left to right along these rows. That's the next rule of the heap. So then we can add, say, a 1 here, C2, 1, and then this row is completely filled up, and we would have to continue adding on the next row. However, what if this value here we wanted to add was not a 1? What if it was, say, a 4? Well, we add it anyway. C2, 1, and that's going to have a 4. Now we check for a violation of the heap structure. The heap structure has been violated because 4 is bigger than 3, and you can't have a child node bigger than its parent node. So what we do is we do something called float up. We swap this value with this value such that the 4 is now the parent node, and this is a 3. And then we check again. 12 is greater than 4, so the heap structure is restored. Now, we don't actually have to check with this child here, because as long as this was already a heap, this child is automatically less than the one we swapped it with. So all we have to do is check the parent and go all the way up to the root, or all the way until there is no, until the parent is larger. And if instead of adding a 4 we were adding a 20, say, we're adding a 20, well, we would float up. So this becomes 20, this becomes 3, and then we float up again so that this becomes 12, and this becomes 20, and the heap structure is restored. Now, you can see how this can work for a sorting algorithm, because once you've added all your data to this heap, all you have to do is take the root away, and we automatically know that that is the largest. So now that we have the largest one, we know to add that to the, if we're going in ascending order, we know to add that to the end of our array, and thus we can sort the data by using this heap structure in a sorting method called heap sort. So once we've got this, we take it away and add that to our, say we wanted in descending order just to make it easier. Let's take that away. Now what do? We've taken something away. Well, the heap structure dictates that if you don't have enough to fill it, well, you take off this thing. You get rid of the one on the end, and that was a 3. So to get rid of it, we'll just swap it with the root. So the root is now a 3. Of course, the heap structure is violated. So what we're going to do is we're going to compare this with its 2 children. First of all, we compare the 2 children, and we see that C1 is smaller than C2, so C2 is the largest child. Now we compare the largest child with the parent, and we see that the largest child is larger than the parent, so we swap them around. So that was a 12. We put 12 down there, and that was a 3. Was it? Hang on. I think so. So we swap those 2, and now we automatically have that the parent is larger than this one, so we don't need to worry about this whole side of the heap. It doesn't matter. Now we just check against the parent, against the children of this new parent, and we see that everything is well and good. So the heap structure is restored. Now we pop this one off the top. So our ordered structure is 2012, and that means that we can get rid of this node. That's 2, so we put a 2 at the top here. And again, we compare largest child, which is a 9, so we swap it. The largest child is larger than the parent, so we swap it. That becomes a 2, that becomes a 9, and then we repeat. And now there is no violation. The child can be as big as the parent, it just can't be larger. So pop the 9 off the top. Take this one away. That's a 1. Compare with largest child. So we swap that one. And you get the idea. And essentially we diminish the heap until there's nothing left, and that's how we know we're done. And we have our correctly ordered list. And if you want to have it in the other order, the smallest first, then it's essentially the same thing, but what you can do is you can represent the heap as an array and diminish the size of the heap as you're adding to the end of the array, such that when it comes out, you fill this array in the backwards order so that the smallest value ends up at the front. And that is essentially how heap sort works.